Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Erini Lambrides with us today. Hey, Erini.
Hello, how are you?
I am doing well on this January 7th, 2022 that we are starting. And so I wish you, may 2022 be a wonderful year for you.
Likewise, and for all who's watching. It's been a rough.
Absolutely. Erini, where are you located at?
So currently I'm in Baltimore, Maryland. I am joint with NASA Goddard and Johns Hopkins University. I've recently defended my PhD in August. So, yeah.
Congratulations.
Thank you.
Dr. Erini.
Oh, thank you. Thank you very much.
Very good. Let's see, Baltimore in January. Is there snow on the ground?
You know, there is a light flurry, but because I am undergoing recovery from my knee surgery, I witness it all through my window. So I just, the weather comes and goes.
No snow angels yet. Well, I hope you recover smoothly and easily from your surgery.
Thank you.
And I think you had a really awesome coffee cup.
Oh my goodness, yes. So one of my favorite space telescopes is Chandra. And I have this mug here that, cool. Yes, it's from the first data release of the Chandra source catalog. And it is very cool. I'm not going to lie. This was found in my department, and somehow it ended up with my stuff, and I wasn't stealing. I don't know how I got it. Okay.
I'm not accusing you of stealing. I'm not accusing you.
I'm just saying. Wasn't stealing.
That's very. I've never seen one of those before, so that's very cool.
I know. I love it.
That's great. All righty. So Erini, then, given that coffee cup, what is it you like to do for research?
So generally, I really care about galaxy evolution and AGN, so growing supermassive black holes. Basically, what is their interplay? How do or how does not the existence of a growing supermassive black hole allow us to infer how galaxies have, grown and evolved over time? And so, a lot of my work has really centered around testing long-held assumptions, finding new statistical methods to be thinking about these problems, and, hopefully maybe providing a way forward of answering some of these questions of how does the evolution of supermassive black holes coincide with the evolution of their host galaxies?
Cool. Awesome.
Yeah.
And that is going to bring us to this very lovely APJ article. Merger or not? Accounting for human biases in identifying galactic merger signatures. And Erini, take us away.
Sure. So this paper, just to give a little context, is basically a method, that I and some of the collaborators have developed to answer one of these long-standing questions and maybe some of the assumptions in the field of AGN galaxy coevolution. So as you can see, we're talking about mergers, and there's this assumption, with rightly so, that galaxy mergers over cosmic time, play a fundamental role in the shapes and presentations of galaxies all the way down to the present day. Maybe they trigger star formation, they change the distribution of the gas and dust in a galaxy. And so because you have all of this gas and dust in these systems, losing angular momentum in these merging events and falling in towards the respective center of these two galaxies, well, you have a supermassive black hole, or maybe that is just merged of these two galaxies or is in the process of merging, and all this gas and dust is being introduced towards them. And how we believe you get a quiet supermassive black hole into one that's growing, or an active galactic nuclei, an AGN, is this introduction of a lot of gas and dust in the very, 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 very center of where the supermassive black hole is. So mergers, were thought of being a way that you could do that, of funneling this gas and dust in. Unfortunately, the results, the empirical evidence is very mixed. And so there is a lot of debate in the field about the role that mergers play in the triggering of AGN.
Okay.
Yeah. And so, some people think maybe it's only the most massive AGN or the most powerful AGN that were the ones that were triggered by mergers, or maybe it was, all AGN, but we're really doing a bad job at identifying which ones are the mergers. And some saying, no, mergers are changing what the galaxy looks like, but the actual triggering of the AGN, isn't going to be dominantly happening from merging systems. And so it's really important we figure out the answer to this question, because, it underpins one of the great unknowns, which is, even identified in the recent NASA decadal survey of how do supermassive black holes grow and evolve over time. And this question of how you trigger a supermassive black hole is unanswered. We're still trying to figure that out. And so we, in a previous AppJ paper, had discovered this amazing sample of sources that were from the Chandra Space Telescope in the Good South Field. And basically, they were representing the most obscured and lowest flux sources really found ever at that redshift range in those numbers. Mm-hmm. And these galaxies represented a really ill-explored portion of the parameter space of AGN. They're less luminous. They're not as powerful as quasars. They're very heavily obscured, which means you can see the host galaxy well, because, usually if you're dealing with a quasar, especially one that is not obscured at all, you're having all of that light coming from this engine growing in the center, outshining the collective billions lights of stars from your galaxy, right? So obscured AGN are great because an AGN is there, but you can also look at the galaxy it's in and do your science that way. So this was a really amazing sample. No one's really looked at their morphology, and this question of mergers hasn't really been applied to them. And what's important about that is these galaxies represent the bulk of AGN in the universe. Especially at these cosmic epochs, they are the less luminous kind. Quasars are amazing, but they're rare. So these really powerful AGN are actually really rare. So if we're trying to find some sort of cosmic mechanism that is responsible for triggering the majority of AGN over time, we need to be looking at representative samples. And so that's where this sample comes in. Cool. So we now have to classify them. Are these galaxies in a merger or not? Because whether they are is going to then lead us to the next steps of the study. Yep. And thus was the motivation for actually taking this very long-winded introduction.
Oh, it's great.
Okay. This deep dive into, how do other people determine if a galaxy is in a merger or not?
Right.
And is there anything we can do to improve upon that? And make our lives easier by being more confident in the numbers that we're reporting at the very end of the day. And so that is the beginning spiel to this study. As we scroll down, basically I start off talking about how there's been this confusion with the AGN and the mergers over time, and as we keep scrolling, some people say the confusion might be due to selection effects, or some might be due to not doing a good job at identifying if something is in a merger or not. And then on top of that, there's also very different statistical methods that are used across these studies over the years of how they want to give the fundamental number that most of these studies try to come out with at the end, which is what is the merger fraction of their sample of interest. So what usually people do is they have a sample of some type of AGN, and they have a control sample that, is carefully matched. And they're like, okay, the merger fraction of the AGN sample is X and of the control sample is Y. If X is greater than Y, mergers are preferentially triggered by merging galaxies. If it's less or equal to Y, or around there, there is no difference between that. And so that's this ultimate number that people are getting towards, which all of galaxy evolution's connection to AGN is apparently being hinged on, is whether this number is going to be greater than or not statistically than this other number. And so you really need to trust your errors in every single portion of that number in order to do that. And so for lower redshift galaxies, I mentioned a little earlier, I was interested in looking at cosmic moon, where the peak of AGN activity is, and really where this method is most applicable. These in earlier in time, or in smaller redshifts, so things that are more local to us, there's really been a lot of advancement with various machine learning and deep learning techniques. So basically, let's take humans out of the equation, train algorithms on robustly defined training sets, and some of them are unsupervised, but most of them are supervised learning, to go and classify our galaxies for us. And unfortunately, there currently really is no black box method of dealing with higher redshift galaxies, and that's because, frankly, it's very hard, and constructing a truth data set at these redshifts is actually very difficult. And so we didn't want to jump to that technique right away. We kind of realized early on that we were going to be tied to humans, that we were going to need to use humans in our study to classify these galaxies, just because of the nature of these sources. And the other plus is that we're dealing with galaxies that have all been observed by Hubble, and deep Hubble images in multiple bands. So we can estimate, especially by looking and comparing to certain theoretical works, well, how well would we be able to see a merger at this specific flux at this time? What is our bias, basically, to the fact that some of the features might be faint? And doing a kind of back of the envelope calculation, that way we find that this should work and this should be fine. And so the next thing we really needed to look at is, okay, how are we going to measure the merger fraction? And the most common way people do it for objects at this source, and I'm going to move myself because as the sun is setting, it looks like I'm in the movie Sunshine with Cillian Murphy. And
yeah.
A little better, a little bit. You know what? Let me just move further on down to this part of the couch. But basically, how were other people doing this? And that goes back to that idea with the control sample, right? It's trusting that they're getting a sample of galaxies that are not AGN, but are similar in every other way, and measuring their merger fraction robustly. And even if they're using humans, humans are biased. We're so biased. Anything history has told us that we're biased. Humans are also notoriously good at finding patterns, even when patterns don't exist. And so the idea with using humans to classify galaxies and whether being mergers or not is like, okay, sure, they have a bias, but if you have them look at a control sample and you just are comparing the difference between the two, the bias should be evenly applied, right?
One would think.
Assumption. Yeah. And so we're like, well, let's test that first. We really weren't expecting what we first found, but we were like, let's just test that because it's a pretty big assumption to make. And it really hasn't seemed to be questioned as much in the literature, at least in what some of the papers that I'd read. And so starting to look at it from that venue. And so that's where we go into section 2, which is the idealized problem and issues with the conventional approach. And so honestly, in this case, normally I don't like jumping into the equations first, but, in this place, I think it says it quite nicely because, really the thing that we're going to do as you scroll down to equation 1 on this page is we're going to be able to kind of look at this problem, just from first order principles, really, trying to parameterize the most basic assumptions with this approach, which is, let's say you're trying to find the merger fraction of a sample. That is the FM hat, right? That is the observed, right? So that is the thing that we're trying to find. And let's say you have humans looking at a sample of galaxies and you don't know which ones are mergers or the converse isolated beforehand.
Okay.
And let's make the assumption, because we do have to make assumptions, we can't be completely assumption free, that the bias of a human can be parameterized 2 ways. Their accuracy at identifying if a galaxy is an emerger or not, that's R sub m, or their accuracy at determining if a galaxy is isolated or not, that's R sub I.
Got it.
So let's say someone has a merger bias. What would that mean? That means if you give them a picture of a galaxy, they're going to oversee mergers all the time. They're going to misinterpret little fluffs as being a part of the merging system. So that's them finding a pattern that doesn't really exist. They oversee mergers all the time.
Right.
And let's say someone who looks at isolated galaxies, and basically they have a problem where they think nothing's in a merger. They really oversee, they really are like, this doesn't seem, big enough to be considered a merger. I think that, companion or fluff, isn't interacting with it or something like that. And so that's R sub I. Yeah. And so this number 1 expression here is basically saying, given the accuracy that someone has about seeing mergers, and F sub m is the true merger fraction. We don't know what that is, right? So we don't know. But basically what we're saying is if we look at in a sample of galaxies where you have some sum of merging galaxies and isolated galaxies that's true, the measured amount of merging galaxies is going to be equal to how their accuracy is affecting what they measure.
I'm with you. Yep.
So we go and we parameterize it that way. And then we're like, okay, and what people do in the end is they also do the same thing for a control sample. So equation 2 is just equation 1 repeated, but now with a little sub c. So it's saying you're going to do the same thing to a control sample. Yep. And then what they're like, okay, what's the difference? Is there an excess of mergers in one sample over another or not? And that's equation 3, that delta. And if you go through and do the math, we find that the term for the intrinsic merger fraction doesn't disappear from the equation. So that's that delta sub FM. Yes. It doesn't disappear. And so what does this mean? So let's go to figure 1 now, because this will now kind of collectivize everything that we're talking about, which is I have 3 different lines here with 3 different examples. The blue line is a sample that was observed by people who were fairly accurate. If you look into the little inset there, there's that 0.9, 0.7. So that's saying they have a 90% accuracy at looking at things as mergers and a 70% accuracy at looking at things that are isolated, and so on and so forth. And the gray line is perfect accuracy. Okay. And on the y-axis, we're measuring what the observed difference is between 2 samples, yes. And the x-axis is the real difference between 2 samples. So we are generating these synthetic simulated catalogs, right, where we know a priori what their merger fraction is, and then we make up accuracies of a magic sample of humans, and we go through and do the math, and what you see here is that none of these lines are showing something one-to-one. You're seeing that there is a difference. The difference between the real intrinsic merger fraction is different from the difference that is measured by humans. And now this basically means, that assumption, that even if you have biased humans and you give them a control sample and a science sample, their bias is not going to be evenly applied because it's going to be dependent on whatever the intrinsic merger fraction is. What does that mean? Well, it actually makes a lot of sense if you think about it this way. Let's say I gave you, Frank, a sample of galaxies, which just so happen to be like 90% merging galaxies. You don't know that. I know that. Right? Yep. And you're amazing at classifying galaxies as mergers. You're too good at classifying galaxies as mergers because you see mergers everywhere. So I give you the sample. Your bias effect on your final number is actually going to be small because you see mergers everywhere and the sample is intrinsically high in mergers. So it doesn't matter that you're bad at looking at isolated galaxies because there's very few isolated galaxies in the sample to mess up on.
Right.
But now let's say I gave you a sample of galaxies that were primarily isolated. Your subjectivity effect is going to be higher on those galaxies because you're telling all these isolated galaxies are mergers than you were in the sample that had more mergers in it. And so now let's look at that into the case of what people do in the field where you have a science sample and a control sample. If your science sample or control sample have really different intrinsic merger fractions, so let's say, the whole thing that people are trying to find, that there's an intrinsic difference, the effect of their bias is going to be different on each of those samples.
Yes.
And that's a problem because now what we have is our final results when we're looking at differences between mergers are not just about the data anymore. It's about the combination of people's accuracies and how they relate to whatever the unknown intrinsic merger fraction is. Mm-hmm. And that is what we needed to fix in order to do our study, to ask that question about whether these low flux HEN from Chandra are mergers or not. Mm-hmm. And so now we go into the next section where, so we go on with this. I think actually, this was basically looking at it in terms of a different way that people might report numbers, where they're looking at the fraction versus subtraction between the numbers. So it's basically saying the same thing. Uh-huh. And so, so basically these two figures are saying the same thing, where, regardless of, what is going on, if you have people who are looking at two samples with two intrinsic differences between the samples, then how much their accuracies are going to affect it is going to vary in a nonlinear way that you can't really just subtract out. You need to estimate their accuracy and incorporate that into your merger fraction. And so that is what we do in the next section, where we're going to take now, we're getting increasingly more Bayesian as we go. Yeah. So the equations get a lot more squiggly as we continue on. So the rest of this, it's pretty much beating a dead horse on, what's going on. And so now we're going to do a Bayesian upgrade to the frequentist approach, yes. The number of mergers likelihood. And so in some of these other studies, what they're looking for is what is the number of mergers in their sample. Yes. And the statistics that they use are binomial statistics, which is basically like Bernoulli trial, yes, no, merger, not merger. And there's a very specific distribution that kind of data follows. And that is when you're using binomial statistics to go and represent the errors on your numbers. And so most of these studies, what they do is they'll have, 5 of their collaborators, 10 of their collaborators go and look at a sample of galaxies and, come back to them with an ASCII file that basically says, index 1 merger, index 2 not merger, index 3 merger. So then, the poor grad student or whoever's on the other end and doing the analysis me goes and, converts these yeses and nos to zeros and ones, and basically are saying, okay, classifier 1 found 5 out of 10 of them were in mergers, classifier 2 found 7 out of 10 were in mergers, so on and so forth. They combine them together, and then they represent this combined number using the binomial statistics, and then boom, they publish what the merger fraction is of their sample. And so we already said, though, well, we can't just do that because there's errors that are not being accounted for. There's biases that are not being accounted for in doing the usual method. So how are we going to account for them? We can basically account for them by finding a way to put a prior or to put an estimate of the error that a given human has when classifying merger galaxies versus isolated galaxies. So the paper is structured in 3 different ways, in 3 ways. So with each of these next 2 sections. So basically the first way is I'm going to make synthetic catalogs where I'm basically just, populating arrays with random numbers under a certain parameter range, and then going through and testing out this mathematical formulation of representing what the likelihood is that a given sample has the number of mergers it has, given how accurate or inaccurate the sample of humans are that are classifying them. And then the second subsection is like, okay, let's take this a step further now. Let's make it more real world. Let's actually get real humans in on this. So this first section, I'm basically going ahead and showing these likelihood functions. So, equations 6 onwards are basically me going in and showing, how we're going to be parameterizing this in terms of the probability onto a likelihood. In the end, we get this statistical model where we're basically treating the accuracy of humans as a nuisance parameter that we need to marginalize over and incorporate so we can get the final result of the number of mergers in a sample that is truly being driven by the data that we have. And so figure 4 is kind of like a graphical representation of this model. So, if you're someone who does a lot of statistics in this kind of way, you might be used to this. But if someone who doesn't, basically, I don't even really need to go into detail with this. Basically, yeah. So, we're just going to keep going on. So I want to get to the fun stuff. Yeah. So testing the.
This was number 2. Then you had the second section, right?
Yes. And so this is that subsection, testing the likelihood model on a simulated galaxy catalog. And so what we're doing here with this one is what, I was mentioning. And before I went and just showed you the math, and then this is the section where I'm just making up numbers and then populating these numbers into the model to test to see what happens. And so in this figure that you see here is basically us doing that, where this was really interesting. This is actually one of the first things that we saw, which was that orange points are representing the standard method, and the blue points is using our merger fraction likelihood model. The y-axis is how many sigma away are you from the intrinsically true merger fraction. So, this is when I simulate X number of humans with Y number of accuracy ratios for merging in isolated galaxies, and they look at N galaxies. What is their number of mergers they get? How does it compare to the real amount of mergers that I know a priori? How many sigma away is it? And what you're seeing here on the x-axis is the intrinsic merger fraction. So I do this a bunch of times at different intrinsic merger fractions. So in this example here, this is looking at, you can imagine having the same imaginary group of people, so it's the same accuracy pairs of merger and isolated, but having them look at things that have different intrinsic merger fractions. So, 0.1 or 10% of the galaxies are in mergers, 0.8, 80% of the galaxies are in mergers. And as you can see, their distance in sigma units away from the truth is not flat across the No, it goes down. But
Also,
we our way of doing this, of being like, okay, let's account for their accuracy, and do things really similarly the same way. We're still using binomial statistics. We're just kind of beefing things up and putting a pretty little bow on it, in a more Bayesian way, to get the numbers. And what we see is that, we're pretty flat, and pretty independent, those blue points, of the intrinsic merger fraction. Okay, great. That's all great, said and done, but this is all not real. There's no real humans. No humans were harmed during this particular portion of this. So now, I need to actually go and test what this would look like in the real world using this method.
Okay.
And so that's when we get into that next subsection, which is testing the likelihood model on mock galaxies with real human classifiers.
Okay.
So I still need a sample where I a priori know the truth. Are they really in mergers or not? So we're going to use simulated galaxy images that I'm going to do the best I can of making them look like real galaxies, as if they were observed in the same exact field, the good south field where my Chandra data is from. So trying to make this analog of simulated galaxies to real galaxies that are going to be looked at in a different paper, because this paper is like validating and kind of discovering this issue and finding a way to deal with it, and have real humans, in fact, the same humans who will be classifying my science galaxies of interest in paper 2 are also going to be looking at these. And so I went and asked a bunch of people who would like to be a part of this. And it is a range of people. So there's, faculty, so a lot of the co-authors of my paper, Timothy Heckman, Colin Norman, Duncan Watts, Kirill, Eileen, Alison Kirkpatrick, Ariana Long. These are all different astronomers, astrophysicists, who are either theoretical or observational in various stages of their career. So you have people like Tim and Colin who are like, have been doing this for ages. Tim is observational. Colin is theoretical. We have a mix. And there's like a side portion where I was just curious, like, who was going to do the best? So to make this fun, I actually made a competition. So after all my classifiers went and gave me their classifications, I told them I was going to measure their accuracy and all these other things. And whoever was the most accurate was going to get a prize. Whoever was the most consistent was going to get a prize. So I basically gave out prizes to try to incentivize people classifying. It was about 180 galaxies in the final. Yeah. And for this paper, it was like the 40 mock galaxies. So I really needed to incentivize them. And so that's what we did. In table 2, I'm basically just summarizing the simulated mock galaxies that were used in the study. And so, anyone could go and look at them in their raw form, but in the appendix, which we don't have to scroll to now, is what I show what it looks like when I add noise to them. They were previously convolved with what these objects would look like if they were looking at the same HST bands that are used with my data, and so on and so forth. And so there's the intrinsic type of a galaxy. That's also there. That's that type. So I isolated, M merger, and F fake. So F fake is when we took 2 galaxies that were at different redshifts, but superimposed them. Okay. So they really aren't interactive. They're meant to present what the foreground, background galaxy. Yeah, don't try to trick them. You know what I'm saying? We gotta make them work for their money. You know what I'm saying? So we gotta mess it up for them.
You gave away money, did you? I've got to. Please volunteer me for the next one.
Giveaway,
I suggest giving them all Chandra cups is what it should be. So
you know what? I'm sure I could find a few more of these in the cabinet at Hopkins. Maybe they'll get. But yeah. So
okay.
They go on this, they measure it, and then we measure the probability of that galaxy given the data of what the accuracies were from our people of being in a merger or not. And that's when we get to the next figure, where I think it's on the next page.
You want 6? This looks like mock.
fun, right? Yeah, because figure 6 is basically the example of this is what the galaxy looks like without noise, and then that's what the galaxy looks like with noise. So it's not very nice, but this is the truth. This is what they look like. So yeah. So and then the next plot is actually the probability distributions of my classifiers, my real people's accuracies. So you could see, the open-faced histograms are their accuracies looking at merging galaxies, and the filled-in ones are isolated galaxies, and each different pane is a different classifier. And so you could see, the one on the lowest right, they're amazing at classifying merging galaxies. Look at that.
Wow.
That's like 90% accuracy. And then they're pretty abysmal at classifying isolated galaxies. They're at 50%. And so it was fun looking at these distributions and seeing, who is going to be the most. So something very funny that showed up, just as an aside before we go, is there was one person on the paper who was a PhD student but was not in astronomy. So they had really never seen astrophysical data images before. I gave my classifiers beforehand a rough guide on what different classifications were and the assumption of like, okay, this is what would be classified as a merger or not, like suggestions of like a very known standard sample of galaxies.
Right.
And so that's all this person had. And they actually turned out to be the least biased of all of them. So their accuracies of mergers and their accuracies of isolated were very similar. And that was interesting. So really, this should really go to say something, because a lot of these really stress that they have these expert classifiers. But by being an expert and by seeing many things, we may be reinforcing certain biases on what we think emerging galaxy or isolated galaxy should look like. Right. And so that was very fun to just kind of go in and, poke fun at, especially the older established people of just, well, wasn't that good for isolated galaxies? So I don't know, man.
You still graduated, so
I did. It was a risky game though. So if any PhDs,
absolutely,
in these footsteps. So as we continue on, we go and we find that our measured merger fraction from the sunrise, that's the name of these mock galaxies, the blue histogram, this is like ugliest plot in the paper too. Oh God, but whatever. We'll show it. But the blue histogram is, basically the probability distribution of my, given my classifiers information and putting them into our model, what are we getting? And so the orange line is the true merger fraction of the Vela sample. And as you can see, the histogram is pretty well centered around it. So that was great. And, we could have said, cool, we're done. And the paper could have ended here because we did what we set out to do. We wanted to find a way to just make it a little better than the original method. Got it. But we didn't.
Yay.
I had this amazing collaborator. His name is Kirill Chernyshov, and he is a stats whiz. And he kind of, me and him constantly, he makes my life, hard because, I'll come in thinking, okay, I figured it out. It's fine. It's good enough. And he'll always come in and be like, but what about X? And yes, exactly. I am so glad he does this because in the end, I think what comes out is a much more interesting and creative way, and I think more correct way of dealing with the problem. And so this next section and the final section of the paper in this is a new approach, simultaneously estimating the merger fraction and the probability of an individual galaxy being in a merger.
Right. Uh-huh.
And so normally, right, I don't know if you've heard, I'm sure other people have had Galaxy Zoo, right? Everyone's like, when they think about humans classifying things, the first thing they think about is Galaxy Zoo because they're like, citizen science did it incredibly well. They had a lot of people involved and citizens who have joined from across the world, looking at all the Sloan galaxies. and classifying them. Now, unfortunately, the Sloan galaxies are all pretty local. So it's also ground-based. So what that basically means is, sorry, rewind. So because Sloan is ground-based, the galaxies that you can kind of see well enough to morphologically analyze tend to be kind of closer. Mm-hmm. So you're not going to be having a bunch of citizen scientists classifying galaxies at cosmic noon as viewed by Sloan. So, but what they do in Galaxy Zoo is they basically have about, they have at least, I think their average number of humans per galaxy is between 24 to 30 humans on average are classifying an individual galaxy. And so what they're able to do at the end of the day is give the merger chance of an individual galaxy being in a merger. And that could be really useful if you're trying to create a sample of galaxies that are only in mergers and you want to select on that as a feature. If you base, there's a whole host of reasons why you would want to do that. Right. But in my field, and with a lot of these, previous studies I've been mentioning, you can't really do that because it's really hard to get 30 scientists to want to sit down and classify galaxies. And also it's unfeasible to do a big citizen science project for just your data set, your one paper, right? And so what usually ends up happening is all these galaxies get averaged in together. And we're really losing the information that you're getting on an individual galaxy. So for example, let's say your classifiers are given, a sample of 10 galaxies and 2 of them are just horrible, really hard to figure out what their merger,
that would be me. I'd be one of those.
But listen, there's beauty in the horror, and that's what's good with this method, okay? Because you wouldn't know the old way if everyone was failing on an individual galaxy easily. You would kind of have to go in and try to, because in the end, they're just giving you their total number of mergers, or the numbers keep getting averaged or squashed down to this representative number. And you're kind of not really incorporating in the error the individual difficulty on a per galaxy basis. So basically, you're just looking at how much does the final number spread compared to the other people. But, what about it on an individual galaxy level? So what this method does is, what is the merger fraction that agrees? So we're not dealing with numbers of mergers anymore. We're now explicitly looking for the likelihood of a sample of galaxies having a specific merger fraction that is in best agreement given what every single classifier said on an individual galaxy level. So that means, let's say everyone messed up on the same galaxy. There might just be something wrong with the galaxy. Maybe I messed up. Maybe I reduced something wrong, or someone reduced something wrong and there's a big streak in it or something, and whatever. And when you start getting into bigger and bigger galaxy samples, you want to be able to have your errors kind of correspond to truly what was more difficult or not more difficult to do. And so with this method, you're able to incorporate that into it and have your final number errors be indicative really of way more sources of error within this of these samples than you really would get before. And so that's what this section was. And so similarly as what we did to section 3, the first part is we're parameterizing the math. It's very similar, but a little different in the sense that basically what we're doing is now breaking it down. As opposed to dealing with the number of mergers, we're looking at what were individual things classified as and looking at the product of all of those and then building that up into the likelihood. And these accuracies that we find for people are, they're priors in this method. And so it's very similar to before, but, different in what number it is we're getting at in the end and how we're using the data. And so in equation 18, that is the probability that a particular galaxy is in a merger. Mm-hmm. And equation 17 is the probability of a collection of galaxies having a merger fraction. So with this, a specific merger fraction. So with this sample, you get 2 of these numbers just by virtue of how we're doing the analysis, which has been very useful for other things. So as we did in the other one, we talk about the math, and then we go on to the next section where we're like, okay, let's test this on just simulated galaxies. And so now we get to look at things a little bit different, because now, as you see in figure 10, I have points now, right? Because I, made up this is before the mock galaxy samples test. So this is just dealing with synthetic galaxies that I made up their numbers. And so the colors are corresponding to whether they're truly isolated and whether they're truly a merger. And on the y-axis, we have the probability of an individual galaxy being an merger, closer to 1, higher chance of being an merger, closer to 0, isolated. And as you see, in a perfect world, every single orange point would be at 1, every single blue point would be at 0. We mostly get that. The accuracy is actually pretty high, and in fact, the accuracy of this method is higher than some of the deep learning methods. So these have this plus and minus to what method you want to use. There really is never going to be one single tool in astronomy that's going to work for everybody. So if you're dealing with moderate galaxy samples at higher redshifts, and have good enough image quality of your data to be confident that you're capturing at least the mergers that do exist down to a certain flux threshold, then this is going to be the method for you, in my opinion. But I am biased, of course, as I have shown.
We'll take it.
Right.
We'll take it. Very good.
Yes. And so finally, we see at the next section, we basically do the same thing, but instead of using my made-up catalog, I'm using real people again on mock galaxies. Okay. And I'm going to close on something so you see we're able to recover the total merger fraction. That number is going to be the least insensitive to some of the issues I'm about to explain. Okay. And in the end, in most studies, what you really want is the total merger fraction, because that's what you're trying to say at the end. You're trying to say, okay, are AGN, more likely to be in mergers or not? So what's the merger fraction of the AGN sample? What's the merger fraction of the control sample? Right. Oh, the AGN are higher, or the AGN are lower. So that's the thing we want in the end. So this is good. We're able to get within a sigma every time. This is an example of, our results with this. And so the blue is the histogram and the orange dot is the truth. And so, okay, cool, great. And now this is, again, this is a very different way of going ahead and do it. And I trust this the most out of everything that I've showed you. And this is what I will be doing whenever I need to use humans in the future. In the bottom figure below it, you see a little bit of mixing of, orange and blue than you would kind of want, right? Because you're like, well, you have, a few mock isolated galaxies that are up at the top, right, and mergers that are at the bottom. What does this mean? And so what I'm going to close on is the utility of this method, because what we found was, and as you can kind of guess this kind of logically, but now we're able to parameterize it in a way which will be very useful for even when deep learning studies need training sets that have errors on their training sets that can then be used so they're not training their models on biased data, is what types of galaxies are people most likely to fail on? And so what we see is the galaxies that people are going to fail on the most, and by how much, are higher redshift galaxies that have just undergone, that have, it's been like a giga-year since they merged. Okay. So they're considered a post-merger. So they've coalesced already, and it's very difficult at that redshift, at around redshift 2, to tell the difference between a puffy galaxy, because galaxies were puffier back then, and a galaxy that has just coalesced from just imaging data alone. And so this is what we're seeing. So the nice. 80% of our incorrect numbers are coming from the fact that everyone failed on these objects. Okay. A single person got it right. Okay. Yeah. And so this was really useful. And so so we end now the analysis on this, and so the TLDR or whatever is the methods that we used to use for this very important number, which basically tells you how AGN get triggered throughout cosmic time according to your favorite galaxy evolution model, may actually have been measured not the best way, and we need to improve on that. And so then we go and we improve on it. We show two different methods. In an ideal world, we probably only would have had that last section, but we don't want to freak people out too much by jumping too far from so we stepped it there in terms of the science story of like, well, this is what you could do if you want to retain like 90% of the assumptions you use in the traditional method. And then here's like, maybe 50% of the assumptions in the traditional method. And so just giving the community options of how they want to think about it or how they want to deal with their data. Because in the end, really, this was a very community-driven paper in the sense of like wanting more tools to be available for people to go and do these kinds of analysis and potentially, hopefully, do them more robustly. And so all the code for this is on GitHub, and we're trying to make it as open science as possible. And so we give people these Jupyter notebooks where they're able to go and put in their own data, and we calculate the numbers for them. The source code is available, so if they want to change our models or do anything different, they can go ahead and do that as well. And we also give people these fake mock galaxy samples that we noise added, so that they can go and test the issues, test the accuracies of themselves or other people, and incorporate that into their own studies. And so that paper, so in terms of future work, that paper I was talking about, in terms of using this on the obscured AGN sample, which another thing, obscured AGN, very few studies are looking at their morphology at this redshift. In fact, there really is only one or two. And almost every single study on obscured AGN at these redshifts find or say that there is a link between them and merger activity. In particular, the very, very obscured ones, Compton-Thick.
Okay.
But because we found this unexplored parameter space of obscured AGN, we didn't know the answer on them. And using this method we developed here, in particular in that last section, we found no.
Okay.
Yeah. And so there's lots of other stuff in that paper as well that we go down that line. But that was the first time you really used this to go into the next step. And so that's led down a whole new branch of research, including what I've written about in my postdoc applications. So if anyone's watching, Erini Lambrides, please hire me. But in the postdoc applications are basically, I am, well, what does trigger AGN? What is turning these AGN on? And how might this change how we look at galaxy evolution as a whole in terms of their relationship with AGN? So that's that. But in terms of the previous paper that we were just talking about, like what is the next steps with that? We are able now to parameterize when and how humans fail as a function of companion. So the mass ratio between the two mergers, redshift, data quality, so on and so forth, in a way where if you're someone creating an algorithm to automatically classify galaxies and you're using a training set which tells you what truth is, and that training set is built off of human data,
right?
You will now be able to have errors associated with that, so your model will do a better job. And so, especially with Vera Rubin coming on, where we're going to be dealing with super, super, super large data sets,
right?
You can't really use humans to look at everything. But how do we ensure those deep learning methods are actually robust and are not being trained on their own biases, that they're then just replicating en masse? And so there's that. And so, yeah.
Very cool. And I bet there are other applications you could apply the same thing to other things that people classify.
Yeah.
Very cool. So it's a bit more general than, I mean, you're applying it to galaxies, but it seems a bit more general. That's
Yeah, and so we're very open, if anyone has an idea or something to kind of, look at it that way or parameterize, be very cool to see it. Yeah, no, for sure. It was really fun. This was my first very just kind of stats paper only, where I'm not really showing real data. And so it was a little out of my comfort zone when I was first writing it, because I was just really, it's just this? Isn't this boring? Do people really want to read this? But it was actually quite fun, and I've had so many interesting discussions about biases in astronomy and how do we account for them, and and so it's been really fun. So
very cool. Yeah. Very cool. Well, Erini, thank you very much for walking us through your very lovely APJ article, and I look forward to seeing some of your future ones where you apply this to, let's say, VRO data coming out.
Yeah. Awesome. Yes, it's super cool. Yeah.
Cool. Nice. All right, everyone, that will do, and I hope this made your astronomy day just a little bit better, and we will see you on the next one. Thank you. Bye-bye.